Going. So, oh, I didn't. There we go. So while this is pulling open, we'll take a look at Canvas, scroll down here. So you'll see these sample questions. I'll also get posted up the first quiz. I may not get this up till tomorrow based off of what we did. Sometimes we go a little bit slower than I think. And so I want to make sure that we've covered everything. I'm asking you questions on it. So I'm going to go back through the last couple of questions and make sure it was stuff that after today's class, we really had time to cover. So I'm not asking you questions over things that we haven't done yet. That quiz will be due at the end of next week. So it should just be over material we've covered last week and this week, mostly this week, probably. We didn't do a whole lot last week. You'll also see that first problem set. So typically what I'll do is I'll attach that Word document. This is kind of the actual assignment. So there's 10 questions, kind of tell you which points, how many points are given to each question. I'll try to call variable names. I'll kind of say what it is, but then I usually kind of put in italics what the actual variable name is in the data set. Okay. So I've got a bunch of different questions using the data set gpa.dta. So you don't have to worry about importing anything here. I'm always going to give you these Stata files. You can just file open from Stata, so you don't have to worry about the import feature. I might have to use it today to show you something, but in practice for the assignments, I won't make you do that, right? You can just open up these data files in Stata. Then you're going to have, right, a do file editor pulled open. Now, usually in class, like today, I'm going to go to my iDrive, and we're going to use this review of statistics. We're also going to use, I had this up under week 1. We didn't quite get there, but this MBA sample distribution. So we're going to use these two files so that you basically are going to start from a blank slate, right? I'm not giving you any code for these assignments. You are having to look at what we've done in class, look at the do files we use in class. So if I was working on this, I'd have open this review of statistics and be like, oh, how do we calculate a mean? Oh, well, I can find the mean using the sum function. I can create a new variable. There are multiple ways for some of these questions to actually get the answer. If I just asked you for the mean, you could use the line of code where you said sum this variable. It tells you the mean. You would then type out what that value was. So if I'm building this out, say for like question 1, and I ask you what the mean is, I would use this kind of comment command. Now, by all means, you can write this up in Word if you really wanted to. I guess you could technically do it by hand and then upload a picture of it, although that I wouldn't necessarily suggest that. You're going to have whatever variable you're trying to find the mean of. Well, just having the code isn't going to tell me how to identify where the mean is in that Stata output, right? So once you run that command, it'll tell you the mean somewhere. You need to tell me, I don't know, the mean is 85.4 or whatever it is. Right? Now, you can also do this in Word once again, or you can use the comments feature in the do file. I would try to do it this way. That way you only have one file to upload. It's going to have all your code. It's going to have all your answers all in the same place. It makes it a lot easier for me to grade, but it also makes it easier for you to see kind of everything's in the same place there. Right? So, and then, maybe the next question, I don't remember what I asked you to do, right? But question 2, you'll have, generate some variable equal to blah, 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 blah. And then maybe I ask you a question about that variable. Maybe I ask you what's the standard deviation. So you say, okay, well, I created this variable. Now I need to summarize it to get the standard deviation. And then you tell me what that standard deviation is, what output Stata told you, what value it told you that standard deviation was. Now, you could have also done this by creating new variables and then looked at the variable and reported to me what the value is. So some of these questions, there'll be multiple ways, and we've looked at multiple ways of doing that in class. Okay? So there's not like always one hard and fast way to do it. Sometimes you can use the sum command here, or you could generate a new variable, right? Is that making sense how you'll kind of approach those homework? Now, I think I have the due date set to be pretty far out. Yeah, so next Thursday, wait, not next Thursday, that's 2 weeks from today, right? So you've got 2 weeks. It'll be due before we start class, not next Thursday, but the following Thursday. So I would not wait a week to work on this because all this is stuff that we're probably already going to have talked about after today's class. Everything that you'll need for this assignment, maybe a little bit, maybe the last question or two we'll have to start with on Tuesday. For the most part, you could start tackling this right now. Right? further you get removed from it, the harder it's going to be to go back, right? But it's the first assignment. I know people are kind of still adding and dropping this class. I want to get us used to using Stata. We'll have a little bit of a big window here, kind of a 2-week period where you can get on and kind of get that assignment done, okay? And then it's file upload, so you'll upload your do files here, or if you do a do file and a Word document, it allows you to upload both, okay? Is that clear? I think I've kind of mentioned some of this before, but I don't know. Since we actually have the assignment here, it's a little bit easier to walk through.
So you were saying like, through like those examples we did past couple of classes, that there's multiple ways to do one thing.
Mhm.
If we do something a different way, you know,
As long as it's correct.
As we get the
As long as you can get, yep. Any other questions? But for the most part, you should have a pretty good idea of what the correct way is based off of the things that we have in the do files that we've covered. Yep. Yeah, this review of statistics will be like your holy grail for assignment 1. Okay. Okay. So I wanted to mention that. Oh, I also already mentioned those practice problems. So if you kind of open them up, or sample questions, same thing. I think it ends with, we're talking about things like hypothesis testing. So we should get there today. Like I said, maybe this will, we might not cover it until Tuesday's class at the very beginning. But after today's class, you should have all the information you need to complete that first quiz. So you'll see that first quiz pop up tomorrow or later this afternoon if I have enough time to just make sure those last couple questions line up with where we've ended class today. And that'll be due kind of a week from today. I'll kind of always give you at least a week to kind of work on those quizzes, look at those practice problems. For this first one, I might even make it a little bit more than a week, just since we're still kind of getting going here. Okay, so not next Thursday, but maybe that following Tuesday, just to give us a little more time early on in the semester. Okay. All right. So we left off thinking about how do we standardize variables in Stata. We talked about z-scores, right? That was taking a value, subtracting the mean, divided by the standard deviation. We looked at some examples of normal distributions. So we'll start here today. So the whole reason we wanted to standardize this, we said we might want to know things like what's the probability if I chose a person or an observation at random, what's the likelihood it's in between two values? Well, I don't want to do the integration. If we actually look at the function for the normal distribution, it's kind of nasty to integrate. But if we can turn it into a standard normal distribution, all that work's already been done for us using something called the z-tables. And I'll have some screenshots of the z-table in a second. And I actually uploaded the file of the z-table to Canvas, which I'll show you as well. So maybe I want to know, okay, what's the likelihood that if I look at a value, that it's 1.29 standard deviations below the mean? So when we were converting these x values into z-scores, the z-scores were always interpreted as the fact that we were subtracting the mean and dividing by the standard deviation. It represented the number of standard deviations away that value was from the mean. So something being 1.29 standard deviations below the mean, what's the probability I see something that far below the mean or something even further below? Well, if I were to integrate that function, right, that standard normal distribution function, it will always give me the same value. It's the same function. I'm using a z-score of negative 1.29. It should always return to me the same value, which I think if we use the table is about what, 0.1? Yeah, 0.0985, so about 0.1. Okay. Is this number looking familiar based off another stats class, hopefully? Right, this is going to be a nice cutoff because this is about 10%. Right, the probability of 0.1 would be about it's 10% likely we saw something this far below the mean or something even further. Okay. So how did I find that? Well, I kind of remember that one off the top of my head. And by the end of the semester, you'll remember these because we start to use some pretty common cutoffs, which are the 10, 5, and 1% likelihood. So those would be like areas of 0.1, 0.05, and 0.0. So we'll see the same values start popping up a lot because we're going to use those same 3 benchmarks, right? But if I was just interested in any z-score, what I would do is say, okay, look, I've got this z-table. I'm going to look up the z-score. I want to find the cumulative probability of the probability I see this z-score or anything to the left of it or below it. So the way I would use this table is to say, okay, the first decimal, negative 1.29, I would go down here, negative 1.2. I then go over to my second decimal as my column heading. 0.909 was the second decimal, right? Where these two meet, that represents the probability I saw that z-score of negative 1.29 or anything to the left. So this is how we use the table. Hopefully this is review. You know, if I wanted to do positive 1.29, right? I have actually two sides of this table. So notice here I've got negative values. Here I've got positive values. Okay. I do the same thing. I go positive 1.29. The probability I see something 1.29 standard deviations above the mean or anything to the left will be about 0.9015. Okay. So I'm going to notice something about these values, which is if I'm using a marker that works, this standard normal distribution, if I look up negative 1.29 as the z-score, first of all, what would the z-score of the mean be? So we calculate z-scores by taking the x value, subtracting the mean, dividing by the standard deviation. What's the z-score of the mean? 0, right? So anytime I have a z-score of negative 1.29, remember, this standard normal distribution is symmetric. It exactly folds on top of itself. What would the area under this curve be? If I were to choose an observation at random, what's the probability it's any z-score? Has to be 1, right? Has to be somewhere in this range. So the area under the curve is 1. So anytime I have a negative z-score, what's going to be true about the probability I see that z-score or anything below it? That probability has to be less than 1. But right, any negative z-score, I also know what would the area to the left of 0 be? If this is a symmetric distribution, the area under the curve is 1. How much is on each side of the mean? 0.5, right? So any negative z value, I know has to have a probability less than 0.5. I think it was what, 0.0985 we found? Now, what if I'm looking at that exact same value, but positive? What would the area to the right of positive 1.29 be? If this is a symmetric distribution around the value of 0, what is the area to the right of positive 1.29? 0.0985. So what would the area to the left have to be? Well, if the area under the curve is 1, and the area to the right is 0.0985, the area to the left would have to be 1 minus that, right? Or that value of 0.9015. So the fact that we're using this standard normal distribution, the fact that it's symmetric, sometimes we don't have to look up things as much in the table. Here, if I had looked up negative 1.29, I kind of actually could have backed out what the probability of seeing positive 1.29 or anything below it also was. Now, I can also use the table if I've got the time, and I can't remember exactly how to do this, but we're going to start exploiting that. Right? Hopefully they showed you, I don't know, talked about this in your stats class, okay? Any questions here before we keep moving? Yeah. Yeah. If this is 0, if I were to fold this on top of itself around that mean, where would 1.29 be? Directly on top of negative 1.29. So the area to the left of negative 1.29 has to be the same as the area to the right of positive 1.29. Once I know that, if I wanted the area to the left of positive 1.29, the area under this curve is 1. If I take an area and I put a line in it, those two areas have to add up to 1. So this area plus this area have to add up to 1. I guess I skipped some algebra there, right? But I would then take 1, subtract this area, and I'd ultimately be left with what's area to the left. Yep. I'm going through things kind of quick. Once again, this should be hopefully a review, so we shouldn't have to spend it as much time. But yeah, if you have questions, stop. Okay. Any other questions on this before we keep moving here? Okay. All right. So we kind of already talked about this. We can look up that value of positive 1.29, find the area to the left there. We looked at different ways of doing that. What if I wanted negative 2.53? So if I want the probability that I see here, a z-score above negative 2.53, this is where in this class, maybe as we move, not quite as much, but it's probably going to help to draw things out a lot. All right. So if I'm thinking about a distribution, and I want to know the likelihood that I see a z value what did I say, of negative 2.53 or anything greater, automatically, what do I know that probability has to be greater than? There's one value, well, two values technically I can say it has to be greater than. It has to be greater than 0.5. I was thinking 0, obviously, but we know it has to be greater than 0.5. Why? What's the middle part of this distribution? The mean always has a z-score of, oh, sorry, thank you. Sometimes I don't hit this hard enough. Right? That z-score always has the mean always has a z-score of 0, so the area to the right of 0 will always be 0.5. So what does the area to the right of any negative z value have to be? Something greater than 0.5. Okay? So I know that it's going to have to be some value greater than 0.5. That's really all I can say at this point, right? Other than that, I'd have to look it up in the z table, okay? So if I'm looking at these options, I only have, first of all, if I'm looking for a probability, what does it have to be in between? 0 and 1. This doesn't make any sense, right? Negative 0.49. We know that it's going to be greater than 0.5, so B doesn't make sense. Now, if I was going to guess, what would the z value be? If it's barely above 0.5, the probability would be barely above 0.5, what would that z value be really close to? 0. So if I'm guessing, it's probably not A, because the z-score we have is negative 2.5. It's pretty far away. Now, we might not be really used to dealing with these z-scores yet, but being 1 standard deviation isn't like pretty far away. Being 2 or more, you're starting to get pretty far away. We won't see z values of like 3, 4, 5 all that often. Okay. So just by kind of nature, we would think if I was guessing here without using the table, I'd probably guess D. Sure enough, let's see, do I have it in here? No. So this is probably my cue for myself to show you where. And I think, I apologize for this, I changed this yesterday. I think you were able to see all the files just fine from the homepage. It's supposed to default my files tab to be able to show to you guys. And I realized for some reason, my other 2 courses, it was already set to be, and it wasn't set for you. I have no idea how that happened, but I changed it now. So you should be able to now go into the files tab and access everything as well. Now I, link everything to the homepage so everything was available. It's just, sometimes it's easier and, to kind of have it organized here. So I dropped the Z and what we'll end up talking about later today, which are the T tables. So for now, we just want to use those standard normal Z tables. I could pull this open. So here's all my negative values. Now here's where I'm going to have a little bit of extra work to do if I want to know the probability that it's greater. Because the table is always going to tell me, the Z table, the probability I see that Z value or anything to the left, less than, right? And even kind of reminds me of that with a picture. So if I look up negative, oh, stop scrolling so much. There we go. 2.53. The probability, or the area to the left, is 0.0057. Well, if I wanted the area to the right, what do I need to do? Subtract that from 1. So it ends up being what? 0.9943, right, which is that value that we had in the slides. Okay. So we'll have this Z table here. Once we get further in the semester, we won't use this as much, like I said, because we'll really use those same benchmark values that equate to probabilities of 0.1, 0.05, and 0.01. Okay. But we got to walk before we can run. So we'll kind of start looking at it here. I think I had a slide here. It's really easy to find the probability of less than because I would just look it up in the table. But let's say we went the other way. If I know the probability it's greater than negative 2.53 is 0.9943, what's the probability it's less than that? Just 1 minus that, right? Or 0.0057. Okay. So we're going to kind of use this idea that the area under the curve is 1 to our advantage. Okay. So some common z-scores I mentioned we'll see pop up a lot this semester because they're like, cut like about 90%, 95, 97.5, 99, 99.5%, right? Or here's the probability format of them. We'll see these 5 values pop up quite a bit. Okay. Any questions over anything yet? Hopefully this is looking somewhat familiar. Well, for the sake of time, we're going to skip this one, although great screenshot here, old Hulk Hogan movie. Let's do one that's a little bit more difficult, right? So, and it kind of answers the first question if we work through this one anyways. if you want to go back and review, you can go through that question as well. So let's say, there's this Mr. Nanny movie. They're thinking about making a sequel. Hulk Hogan's making a comeback. And you've got demand for popcorn at this theater is between 50 and 100. And you're trying to say, okay, and this could be like, this makes sense. If I'm any company, I want to try to predict what demand is, and I know that it follows normal distribution. I want to know what's the likelihood if I were to make between 60 and 40 pounds, right? Actually, here I said, what's the probability that they make, that the demand is going to be over 60 or under 40? So if I make somewhere between 40 and 60, what's the likelihood that demand was actually not in that range? Okay. So I would probably try to write things out in a word problem like this. So here I've got, right, my demand followed this kind of, well, actually, normal distribution, had a mean of 50 and a variance of 100. So the way that we write out normally distributed variables in general, I had this kind of last class, was here's their mean, here's their variance, okay? So I'm wanting to know if I were to make, I don't know, popcorn, and we're measuring demand in terms of pounds, what's the likelihood that demand is somewhere below 40, but somewhere above 60, and I know that the mean of this normally distributed variable is 50, right? So I'm looking for this area, the probability it's less than 40 or greater than 60. So what I'm going to do is turn this normally distributed variable into a standard normally distributed variable, or z-scores. Well, I know the mean would actually have a z-score of 0. Here, if I'm calculating a z-score, I take the x value I'm interested in, subtract the mean, divide by the standard deviation. So what is the x value I'm looking at? 40. What's the mean? 50. What's the standard deviation? The variance is 100. Standard deviation is the square root of that, or 10. So negative 10 over 10, this would be a z value of -1. Right? Now, if I'm thinking about my other value, if I want to turn that into a z-score, kind of skipping some steps here, but it's kind of easy to see. How far away from the mean is 60? How far away from the mean was 40? So it's going to have the exact same z-score, except for what? It's not 10 below, it's not 1 standard deviation below the mean, it would be 1 standard deviation above the mean, right? So I'm going to go to my table, and I'm going to look up negative 1.00. Once I know this area, how would I find this area? So the area to the left of -1, what'll be true about that relative to the area to the right of +1? Exact same value, right? So I'm going to go ahead, look up, where did I have it? There we go. Negative 1.00. So my second decimal is 0. My first decimal is 0. Negative 1.00, 0.1587. Okay. So I've got this area here, 0.1587, which means the area over here has to be 0.1587. I add those together, I'm getting something approximately close to 0.32, right? Without mentally straining my brain too much looking at those 4 decimals, okay? Any questions on this? Okay, so just assume that that was 0.32 just to make this point. If I did make, right, some amount of popcorn in between, what's the likelihood that demand was somewhere in between 40 and 60? How would I find that? Yeah, the area outside of this range is 0.32. The area under the curve is 1. This area would just be 1 minus 0.32. Okay, so I think drawing it out starts to, you can kind of see what pieces you've got and what pieces maybe you're looking for. You don't have to draw it out, I guess, if you don't want to, if you can visualize it, but I think having a drawing always kind of helps. Okay. Any questions on that before we keep moving here? Okay. All right. So we're doing all right on time. Go through one more thing before we go to sampling. So if I were to calculate a z-score, this was the equation we were using. We're subtracting the mean divided by the standard deviation. I can rearrange that a little bit so that I can work the opposite way, right? So maybe I say, I think the example I have in the next slide is test scores. So I might want to say, what test score would be the 90th percent cutoff, right? What test score would put me above 90% of other students? Well, as long as I know the mean, and as long as I know the standard deviation, I'm going to rearrange this equation, right? So that I can always back out what the X value would be that gives me a certain desired probability. Why? Because every z-score is connected with a probability, right? So I think that's the example I have, and I'll draw it out for you. Let's say I have a test. I don't know, maybe it's the exam, and the average is a 72, the variance is a 64, and I want to know what's the lowest possible score that would put me kind of in the top 10%, right? So how would I find this? Okay. Well, I know that if I were to convert this test score, so if I have it and it's just regular normally distributed variable, I think I said the mean was 72, and I think I said the variance was 64, which means what would my standard deviation be? Yeah, just the square root of that. So 8. I'm looking for the value that would be the cutoff for the top 10%. So this probability, right? There's only 10% of students, or 0.1, probably a 0.1 that a student selected at random is better than me, which means the area to the left would have to be what? 0.9, right? I'm better than 90% of students, right? If I'm at that 10% cutoff, right? That only 10% of test scores were better than mine. So what am I going to want to do? Well, I know that if I were to convert this variable into a standard normal distribution, or a z-score, right, that whatever value this is, right, there is some z-score associated with having 0.9 to the left of it, right? So I'm going to use my table, and I'm going to work in reverse or the inverse, right? So here, I no longer have a z-score. I know the area in my left tail, right? That area in that left tail below the value I wanted to find was 0.9. So I'm going to have to hunt through here and find what is closest to 0.9. Looks like I'm in between these two values. So this is where we're kind of constrained at 2 decimals, right? That if I'm using the physical version of the table, I can't have like a 3-dimensional table. But I'm in between these. I know that the z value is going to be what? 1.28 and 1.29, somewhere in that range. If I ever ask you a question like this, if you're in between 2 values, always just default to use the higher of the 2. Okay. So in between 1.28 and 1.29, we'll use 1.29. Okay. So using that value of 1.29, right, we said the inverse equation was just rearranging here that z-score formula. So what is our mean? 72. What's the z-score? Positive 1.29. What was our standard deviation? 8. I don't know. This is going to be what? 82 something. Probably have in the slides, right? But I can work in reverse as well, or the inverse, right? Knowing the area that I want, I can find the associated z-score and then back out what value for my original normally distributed variable would give me that. Okay. Questions over anything here? Okay. So, kind of go here, go back, and I think that's what I have right here. I think I was a little bit more precise here. I was probably using like Excel or something, so I wasn't constrained to the table to find 2 decimals, but I still use the 2 decimals down here, right? We said if I was in between 1.298 and 1.29, I'm not getting exactly 0.9, but I'm getting really close. Okay. Any questions on this before we keep moving? Okay. All right. So make sure we have some time to go through this. Well, I'm going to wait and do the state of work later. So, oops, I think I have it in here. There we go. I'll do the jump into state after we kind of go through it. So this whole setup was thinking about, and I was always using Greek letters. So we're kind of inherently using what type of data? We said Greek letters represented population data. More often than not, in fact, 99% of the time, we only have sample data, right? So, instead of using capital N, sample data, the total sample size in our data set will be lowercase n. Really not a whole lot different, just notation here. We assume that every single observation is coming from the same distribution. So this is like IID assumption. We'll dive in this later on in the semester. But for now, we're just assuming that when we're getting this sample data, it was collected essentially randomly, right? That no one person was more or less likely to end up in this sample data set from the population. Okay. So, how can this be violated? So a lot of the times, I think there was like an old study where they were looking at some type of health metric. And if they selected a person at random, they then asked if there were other children in the house. So they were collecting data on children. They asked if there were other children in the household. If there was, they would just throw them in the sample. Well, what that's saying is that given that the first person was randomly selected, it made it way more likely that the sibling was, right? So it wasn't completely random. So all we're saying here is that given the other observations that are selected, every other observation being selected does not depend on it, right? That it's completely random. We don't have to worry too much about the notation here. I'm being a little bit formal in it, but just that it's truly random, these samples that we have, okay? So we're going to write out the mean. It just looks a little bit different. Instead of kind of using the Greek lettering, we'll use kind of y bar. So y is going to be the variable we want to find the mean of, right? Y bar is going to be the average, right? Or our sample average or our sample mean. We're going to do the same process. We're going to add up every single from the very first observation to the very last observation in our sample data set, all the values for this variable y, and then divide by the total number of numbers we added up or the total sample size, right? Or the total size of our sample data set. So notation looks a little bit different than the population, but the procedure, like mechanically, it's the exact same thing. Okay. We're then kind of writing this a little bit differently because we have sample data. If it is that we're selecting people at random, we might not call it the mean. We might call it like the expected value, right, of y bar, or the expected value of the mean. But it's really pretty much the same, right? Now, if I were to take 1 million different samples, so let's say I was interested in like the average height in this room, and I start randomly selecting 5 people and calculating the average height. So I select 5 of you, write down the average height. Select another 5, write down that sample mean. Another 5, write down. Well, they're not all going to be the same value, right? I'm randomly getting different 5 of you every single time. But if I were to look at all of those, so let's say I randomly selected 5 people 100 times. Well, I now have a data set of 100 sample means. Those sample means should always be normally distributed around whatever the true population mean is, right? Now, sometimes my sample might have a slightly higher mean than the average. Sometimes it'll be slightly lower. Sometimes it'll be really close to the average. Sometimes it'll be a little bit further away down the other side. But if I were to plot out, and in theory, if I could take an infinite number of samples, right, those sample means will be normally distributed around that population mean. Or the expected value of my sample mean is the population mean, okay? And I'll prove this to you with some data here in a second. So if this is the case, we're going to say that our sample mean is going to be an unbiased estimate of what the true population mean is. That on average, when we look at sample data, it's going to tell us or reflect to us what the population value should be. Right? Now, it might be a little bit off if we're only looking at one sample, but we know that if we could continue to sample over and over, those samples on average will give us an accurate measure of what that true population mean is. Okay? Now, the variance of our sample means is a little bit different, right? It's not quite the same calculation, we would go through and calculate the variance the same way we were with population data. We would take each observation, subtract the mean, square it, add them all up, and then divide by, not the total number of observations we had like we did with population data, but we would divide by the total number of observations kind of minus one, right? Yeah, but we'll get to that in a second. So if I were to sample like over and over and over again, 5 of you from this group, the variance of those sample means that I collected will not be the same as the variance of the original data. So think about it this way. If I looked at the height of this room, you know, I don't know, maybe it ranges from 60 inches to, I don't know who the tallest person would be. Let's say you're like, what, 6'6", so we've got, what, 78? So we have like a pretty wide range of values. Well, if I select 5 people at random, what's the likelihood I get an average of 6'6"? Not very likely, right? So as I take higher and higher samples, if I take 100 people, now what's the likelihood I see a sample mean of 6'6"? Even less likely. So as I increase that sample size, the variance on my sample means is going to be lower and lower, right? If I were just to like randomly sample one person, well, then I could very easily see someone who is 6'6". But if I select 100 people, very unlikely I'm going to get a sample mean that is 6'6". Right, or 78 inches, whatever that is. Okay. So the variance of our sample means will be the original variance of the data we sampled from, the population variance, divided by our sample size. Okay. All right. And this is, you know, to be technical, called the law of large numbers. We would say now, not only do we have an unbiased estimate of what the true population mean is, but we're also getting a consistent estimator. Right. I'm not going to quiz you on this or anything, but just to kind of be formal here. Okay. So I'll show you some numbers and then we'll jump over to state and I'll kind of prove some of this to you. Okay. So if I were to look at the population data, I had some old NBA player data and I had height, right? So I was looking at what's the average height of an NBA player in the 2015-16 season, right? Doesn't have to be NBA, it could be a country's height. It's just, this is free data, right? So I have a variance and I have kind of like what the true mean is of this Y variable, okay? I'm then going to take 1,000 different samples of size 10, calculate the sample mean, and then look at what's the mean and variance of those 1,000 different sample means, okay? Now, if I'm truly selecting these at random, what should the mean of these 1,000 different random samples be? Population mean. What should the variance be? The original population variance divided by my sample size. So instead of 12.59, it should be 1.2, right? Sure enough, that's exactly what I get, right? And I'll show this to you with an actual data set here in a second. So let's go. And I've got this NBA. I wouldn't worry about running this along with me today, this part. I'm not going to expect you to do something as complicated as what this code is, but I'll explain what it does so that we can see what I'm saying. A lot of the times in this class, instead of going through like all the mathematical proofs, I'll just show it to you with data, right? If you're really interested in the mathematical proof side of it, by all means, ask me. I can kind of point you to some books or something that have it. But I always like to prove to myself things with data, right? So I'm going to have to set my global, which, let's see. Once again, the easiest way for me to do this is open up the data set the first time. It then automatically tells me what that file path is. So someone asked me kind of why I did this. They stopped by my office. And I just like to do it because if you're ever going back to these files and you do want to recreate things, I always try to write them in a way that it has like, doesn't have my, like it puts the path in here so that you can always just replace my file path with yours. And then the do file should run just fine, right? So if you're kind of using, I try to write everything so that you can use this path global, set that global path so that you can run it yourself, right? So I've got this global path defined. The very first thing that this did, it just opened up that data set again, right? It's basically, notice, it's doing the exact same thing as if I did this manually going to file and open, okay? And we talked about this last week. So I'm going to, just to make it easier, only like this had a bunch of different variables in it, right? Not really worried about all of them for this example. So I'm just going to keep the player's name and what their height was. And then going to summarize that height. And this is where I was getting that value of the mean was about 79.14, variance was about 12.59. That's where I got those values in the slide. Okay, so that summarize command very quickly tells me the mean and the variance. Okay, everybody with me up to this point, because this is where it gets a little bit tricky. Okay, so this is where I'm showing you the power of what Stata can do without necessarily expecting you to do this, right? So you can create, so remember when I said you had to use egen, and it was when you were using built-in commands like the mean, where it then, okay, if I see mean, it knew what steps to do. It knew that it wanted to go through the observations, add up every single value, then divide them by n. Here, I'm defining my own program, right? So I'm going to define this program called y bar, which essentially it's opening the data up, the population data, randomly sampling 10 of the observations, saving them, calculating the mean, and then storing it. Okay. So it's then going to do that 1,000 different times. So it's going to run this program and randomly sample 10 different players, calculate the mean, keep that number. Randomly sample again 10 players, calculate the mean, save that number. Randomly do that 1,000 different times. So I should end up with a data set that's 1,000 different sample means. Well, if I have 1,000 sample means, so let's say I run this program. Takes a second. Right. Here, notice here's all of my sample means. Okay. So if I have this data set with 1,000 different sample means in it, how can I find the mean and the variance of those sample means? What command could I use? We just used it up here. Summarize, right? Or shorthand, I think I did it last class. Just the sum command. It's just a shorthand way. It's the same thing, right? So I'm now going to summarize these sample means. If what I was saying in the slides was true, the mean of these sample means should be that original population mean of, now I already forgot what it was, 79. And the variance, because it was sample size 10, should be the original variance divided by 10, or 1.259. So I'm going to go ahead and do that. Sure enough, the mean, not exact, right? But very close, right? 79.143. Well, actually, out to the fourth decimal is where I have to go for it to be just a little different. And that's because in theory, the theory is actually not for 1,000 sample means. The theory would be for if I could take an infinite number. Well, I'm not going to sit here. Well, can't even really do infinite, right? So I can get close, right? The more times, if I were to do this 10,000 times, it'd be even more precise, right? And then the variance, once again, it won't be exact. We said it was going to be about 1.29. It's a little bit off, right? But once again, that's because theoretically, I don't need 1,000 different sample means to prove this. I would technically need an infinite number. But I think this on its face shows like what we're saying is true, okay? Any questions there before we keep moving? Once again, I won't make you recreate this. This is just a way of proving this or showing you some different things you can do in Stata. So the next thing I want to do is run the exact same code, but instead of samples of size 10, I want to calculate the sample mean of samples of size 30. So how is that going to impact the mean of my sample means? Doesn't. Yeah. The sample size doesn't impact that expected value or the mean of my sample means. The mean of my sample means should always be the population. Think about why. Let's say I took samples of size 1. In fact, let me prove this to you. If I take samples of size 1, what am I really going to end up with? Just 1,000 different random samples, 1,000 different individuals. I'm basically ending up with a data set that just has the individual's heights, right? So if I were to run that same program, oh, I have to clear it first, sorry. I'll end up seeing, oh yeah, the mean is still right around that population mean. Now the variance really hasn't changed because I'm dividing by 1, right? Now, if I do samples of size 30, the mean of my sample means shouldn't change, but the variance of my sample mean should now be what? Higher or lower? Yeah, I'm dividing by 30 instead of 10, right? So now my variance should be a little bit lower. Sure enough, if I run this code, the mean of my new sample means is still 79.12, but the variance, instead of being like 1.29 or whatever it was, is now 0.42, right? And I could kind of continue. Did I do more? Yeah, I did 100 here. So once I get to 100, now the variance will not be 12.59, but that divided by 100. So it should be like 0.1259. So I can run that to kind of prove this to myself. These samples of size 100 now takes a little bit longer to run because the samples are bigger. I didn't think it would take this long to run, so well, maybe we'll be waiting here for a second. Oh, hold on. Okay, thought maybe I got stuck. I changed something here. I went to 10,000 reps, so I was like, oh shit. But yeah, you don't want to have this too big, otherwise it's going to take a really, really long time. But apparently not too long. Once again, the mean of my sample means right around that 79.12. And now the variance is whatever the original variance was divided by 100. So we can prove these things to ourselves using data sets. But ultimately, what we care about are these sampling distributions. I'm thinking about these sample means. They're always going to be centered around whatever that true population mean value is. So for here, let's say this was sample of size 10, right? If I were thinking then of samples of size 30, what's going to happen to the distribution? Yeah, remember, my variance of these sample means is just the original variance over my sample size. So if I go from 10 to 30, the variance is going to go down, which means values closer to the mean are going to be more likely. Values further away, a little bit less likely. Right? And then if I wanted to do samples of size 100, well, now what's going to happen? I get an even more peaked distribution, right? So what does a more peaked distribution really tell me? That if I'm just looking at one of these, it's more likely that I see the values that are closer to the true population mean. Because in practice, I can't go out and gather 1,000 different samples data sets. I usually only have one. So what do we want to ensure? We want to ensure that that one sample data, the probability that it's really close to that population mean is really high. How can I do that? Making sure that my sample is what? I'm going from 10 to 30 to 100. It's getting more peaked, making the values around that population mean more likely. If I can only have one sample, I want to make sure that it's really big, right? As large as I can possibly get. Yeah. Yeah. Right. So I want my variance to be small because my variance being small is telling me that seeing sample mean values further from the true population mean is now less likely. Well, that's good. I want my sample to be as reflective of the population as, because I would love population data, right? More often than not, if we had the population data, we don't have to worry about this, right? We just don't, more often than not, only have sample data. So we want to ensure that sample data is going to give us statistics as close to the true population statistics as we can possibly get, which is why we want that distribution of the sample means to actually have a variance that's very low if we can. We can't really influence that variance, like the variance of the data, the original we can't change that, right? Human height has whatever variance it does, but we can take larger samples. That is the one way we can influence that. Yep. Any questions on anything there? Okay. All right. So moving a little bit slower. Might have a little bit more review next class than I thought, but that'll be okay. I'm not going to waste too much time here because like I already mentioned this, right? Our estimates are a little off. I already mentioned because theoretically we wouldn't need 1,000 sample means, we need an infinite number. So pretty close. We said as we get larger and larger sample sizes, we're getting values that are closer and closer to what that true population mean is, and we're driving that variance essentially on our sample means down to 0. So the central limit theorem is going to be something that we kind of connect the population to the sample data. So I had samples of size 10, and then I went up to 30. I kind of shouldn't have done that because samples of size 10 don't really actually, they break the central limit theorem. In order for our sample means to be normally distributed around the true population mean, technically we need samples of 30 or greater, right? So if we can get samples over 30, we have what we call asymptotic normality, or that our sample means will be normally distributed around whatever that true population mean is. So we shouldn't be dealing with data sets even remotely close to 30. We're going to be dealing with large data sets this semester, so we usually don't have to worry about this. Inherently, we never have to check to make sure the central limit theorem is met. Every data set we use, we're going to have more than 30 observations. So it's always going to be met for us. So I don't know, I kind of pulled this from a textbook that I like because I just think it helps kind of show. If these were it doesn't matter what. So I think I started out, I told you last class, human height is already normally distributed. But let's say I were to take something that's not. So let's say I were to take something like, maybe I just want to look at like the proportion, like gender breakdown, male versus female. That would be a 0-1 variable, right? So it's not continuous. It's not normally distributed. It actually would have like a distribution that would just be like 2 bars, right? So it doesn't matter what the original variable starts out distributed like. So here I've got a, kind of bimodal distribution. I don't even know what that one would be. I've got kind of like a, I don't know, reverse exponential. I've got a uniform. It doesn't matter what the original data looks like. As I start to take samples that are larger and larger, the mean, if I look at the distribution of my sample means, once I get to 30, notice these are all normally distributed. And in fact, if I continue to go past 30, they just become even closer and closer of an approximation to a standard normal a normal distribution. So, if I only take samples of size 2, that's not necessarily the case. But if I can get to 30 or higher, I'm golden, right? So we already looked at this in Stata. I kind of jumped ahead a little bit, and we kind of did all this work. So this kind of is our summary slide of what we just talked about, right? The mean of my sample means is the true population mean. The variance of our sample means will be the original variance over our sample size, okay? So now we have a second problem, right? Okay, you're telling me we have sample data. How can I calculate what the variance of my sample means are if I only have sample data? How do I somehow know the population mean, right? If I don't have the population variance if I don't have the population data, right? That doesn't make a lot of sense. So it's a good question, right? We basically are going to have to kind of get as close to approximation as we can get to it, which is we know that we can't use the population variance. We don't have the population data, but what we can use is our sample variance. From whatever sample we have, we can use our sample variance. Okay? Now, our sample variance is always going to be a little bit skewed because we don't have all of population, right? So it looks very similar. If I want the standard deviation of my sample means, it's the original variance, but not population. The best guess I have is the sample variance divided by the sample size. And then if I wanted the standard deviation, right, I have to take the square root. Right? So the only thing that really changes, instead of using that population variance, I have to calculate the standard deviation of my sample means using my sample variance. Now, the problem is, if I do that, do I have it here? No. So we're not really going to focus too much on this, but if you go back to your stats class, and just to kind of give you an idea about why this is the case, when you're calculating a sample variance, usually you would divide by n. With sample variances, we divide by n-1. So what that does is essentially, try to think of it's not a technical way of saying this, but kind of getting at the intuition. It's accounting for the fact that you could have some outliers in your data set, right? And so it's always, if I divide by n-1 instead of n, what is that always going to do to my sample variance? If instead of dividing by n, I divide by n-1, I'm dividing by a smaller number. So my variance is always going to be a little bit exaggerated, right? Which once we get to doing things like hypothesis testing, we'll understand that makes it basically a little bit less likely that we're going to find that we're going to be able to say that we can reject nulls and things like that. Okay. So the fact that we divide by n-1, right, matters. Because if I divide, let's say I had 10. If I divide 10 by 1, that is 10. If I divide 10 by 2, that's 5. Cut my variance in half. Well, if I have 10 divided by 10, that would be 10 divided by 9 is what? 1.1. That difference isn't near as large. So the sample size will kind of influence how far off that variance would be, even if I did have the true population data, right? Because I'm dividing by n-1 instead of n. So it's going to cause something called degrees of freedom. Basically, we're not going to be able to use the standard normal distribution. We're going to have to use these things called student t-distributions. Everything we actually do the remainder of the, well, from here on out after this week, we'll really be using the student t-distributions, okay? And that is that when I calculate things like when I standardize these variables, I'm not actually getting z-scores or z-values. I'm actually getting student t-values. So there's going to be a set of distributions, right, when I standardize variables, that if I'm using the sample variance, because I don't have the population variance in practice, right? That's what we were needing earlier today. When we were calculating z-scores, I was dividing by the population standard deviation. Here, we're only going to have the sample standard deviation. So what that's going to do is it's going to slightly skew those standardized values so that they won't be standard normally distributed. They're going to follow what we call student t-distributions. And there's not one student t-distribution. Every different sample size is essentially a different student t-distribution. Now, they're all normally distributed, and they're all going to have a mean of 0, but they won't have a variance of 1. The variances on our student t-distribution are always going to be a little bit higher. They're always going to be a little more inflated. Now, as I get a higher and higher sample size, in my point earlier, dividing by 1 instead of 2 makes a big difference. Dividing by 9,999 instead of 10,000 doesn't do much, right? So as we get higher and higher sample sizes, really anything over 100, you can't tell the difference between the standard normal distribution and a student t-distribution out to the like 4th decimal. So if we can get larger data sets over size 100, we inherently, yeah, technically we're using student t-distributions, but we can use the standard normal distribution values to approximate it, right? Because it's out to the 4th decimal, looks no different, okay? Any questions here? I know I'm going through this quick, but hopefully this week is a review. I'll slow down as we introduce hopefully new material kind of next week. Okay. All right. So I already mentioned this, right? If we had our standard normal distribution, our student t-distribution is a little bit more spread out. So kind of to our point earlier, if it's more spread out, that means its variance is a little bit higher, which means values that are closer to the mean, a little bit less likely. Values further from the mean, a little bit more likely. Okay? Now, if I get really small samples, that just kind of, makes it even less likely I see values near the mean, even more likely I see values further away. Excuse me. So we really do have like a set of student t-distributions, but hopefully most of the data sets we're using, we'll be able to use that standard normal to approximate. Okay? Now, the reason why this matters, and the reason why when we start to look at Stata output, Stata can always look at the student t, doesn't have to approximate for us. The reason why this matters is because, and I don't really like my slide here, so let's do this. So if I have a standard normal distribution, we said earlier that value of 1.96, the area to the right of it was approximately 0.1. Right? If I have a student t distribution, and I'm going to really draw this exaggerated, so it's not really this different, but here we go. Right, so let's say this is my student t, and maybe it's because I only have a really small sample size, and then the black one, this was our kind of standard normal distribution. If I use that same value of 1.96, so if I go 1.96 standard deviations above the mean, what's the probability I see something 1.96 standard deviations above from a student t distribution? Well, if this area was 0.1, I'm seeing something that is going to be much greater than 0.1, right? So now these different standard deviations away from the mean, they're going to be associated with different probabilities, right? So it matters that I'm using that student t and not the standard normal, because I'm going to have to use to get 0.1. I can't go 1.96 standard deviations above the mean. What am I going to have to do? If this area is greater than 0.1, I can't go 1.96. I'm going to have to go even further, right? I'm going to have to reduce that area down to 0.1 by taking a higher value. So the student t values that correspond, I don't know, I'm just going to choose a random number, but the student t values that correspond to getting that same area of 0.1 in our tail are going to be greater than the values we see from that standard norm. Okay. Make sure I put the right caps and the right markers here. Any questions on this idea here? I'm getting worried because I'm not getting a lot of questions here today. Feeling okay with this so far? Okay. All right. Oh, for the sake of time, what do I want to do here? Man, hypothesis testing. What do I have in this review file? We covered this last class. Yeah, we already standardized stuff. Okay. We can round this out. So here's like a abbreviated version of the student t distribution. So notice if I can get an infinite sample size, the values that correspond to different areas in the tail, these are going to be the same values we find from a standard normal. In fact, I have the student t distribution up here on a file on Canvas. So let's say the area I wanted, when we were going back to like that popcorn example, or not popcorn, the test score example, we wanted 0.1, right, that 10% cutoff. So the area that I might want in the upper tail, the student t distribution table is a little bit different than standard normal, is that it always looks at the right side, right? So if I want an area of 0.1, how many standard deviations away do I need to go, or what t value, or there's similar interpretation as a z value, would I need to go to get that 0.1? Well, here I want the area of 0.1 in my tail, right? Now, the t value that would give that to me is going to depend on what my sample size is, which really not technically is a technical term here. It depends on our sample size, but the way that the table, and if you look things up about the student t, it actually depends on the degrees of freedom. Well, the degrees of freedom is just the sample size -1. So I mean, I don't know, to me, it's kind of trivial, right? If I know the sample size, the degrees of freedom is always just that -1. So technically, you know, my degrees of freedom here, it's implying I have to have a sample of at least 2, right? And then my degrees of freedom for the very smallest sample I could have of 2 would be 1. So as I get larger and larger sample sizes, I'm getting larger and larger degrees of freedom, the t value that would give me 0.1 in the tail starts to become smaller and smaller until I get all the way down here, and notice at that infinite row, the value that would give me 0.1 in the tail, remember when we looked it up in the z table earlier, I said it was in between 1.28 and 1.29. If I was using a program to be very specific over what that value is, the value it would have been is 1.282, right? So this last row of the student t table, essentially, these are going to represent what? Not t values, but z values, right? And it gets kind of weird because it's infinity, but like if I had an infinite sample, I mean, if I had an infinite sample, I would have everything. So what would I actually have? Population data, right? So it's kind of a weird thought experiment. We never actually truly have an infinite degrees of freedom. In fact, we couldn't, because even if I had an infinite sample, infinity -1, now we start to talk about like different sets of infinity, which does exist. You can take like a, what do they call them? Not logic courses, real analysis course, and you start to think about like comparing different infinite sets. It's not worth your time. But this would be, this last row is essentially our standard normal or our z values, okay? All right, so the next thing we'll talk about, kind of leading us up into next class, is we're going to start doing things like called hypothesis testing and building confidence intervals. These terms sound familiar? Hopefully, okay? We'll add a couple of things in maybe you didn't talk about. Now, we have one-tailed tests, right? So this is the idea that I might want to test for whether or not, maybe I'm interested, is the true IQ of an IU student greater than, I don't know, 105 or something, right? Well, I take a sample, I look at my sample mean, I compare that to that hypothesized true value of 105. If the sample mean is greater than that, do I reject for sure? Do you remember? No, right? Because I still could have, right? I have a distribution. I only have one sample. So I have a little bit more work to do, but I'm looking for, do I find evidence that goes against what I assume to be true? Okay. So what we're going to assume to be true, we're going to call that H subscript 0, or that's our null hypothesis. Okay? So if I can find sample evidence that proves the alternative hypothesis, so here I wrote it as H subscript 1. That's a little bit mathy. A lot of the times in like economics, the alternative hypothesis will just H subscript A. So it's just notation differences. We really won't use for a while too much of these one-tailed tests, right? Once we get to F statistics, things like that, we'll kind of go revisit them. But for the most part, starting out, we're really going to focus on these two-tailed tests, okay? Now, I'll show you some examples of one-tailed tests just as review. But really what's going to be more useful for us moving forward in the semester is we're going to have some value. We assume the mean is equal to some specific value. And then based off of our sample mean, our sample evidence, do we see anything other than that? If we do, is it inconsistent enough with what we assume to be true that we can actually reject that assumption, right? So maybe I assume the average IQ of an IU student is 105. I go out, collect information. I find that it's 103. Well, maybe I can reject that the true mean is 105. Maybe not, right? Because we have a couple more steps to go. But I at least found evidence that was inconsistent with what I assume to be true. Okay. So once I find evidence that's inconsistent with what I assume to be true, I mean, if you think about it, if I assume that the average IQ is 105, if I take a sample of 50 people even, what's the likelihood I see exactly 105? Technically, the likelihood would be, if I have a truly continuous variable, I'm going to really hammer home some infinity stuff today. I could actually see an average out to any decimal. So what are the possible values I could see a sample mean be? Infinite. So what's the likelihood of any one value? 1 over infinity, and the limit is? So the likelihood I see exactly what I assumed is 0. I'm always going to see a sample mean that maybe even I see 105.000001. Well, that's still technically inconsistent with what I assumed, but it's not very inconsistent, right? I know that if I'm that close to my assumption, it's probably that I just happen to have a sample that was a little bit different from the population, right? So what we're going to do next is take whatever sample mean value we see and say, okay, how many standard deviations away from that assumed true mean is it? So mu subscript 0 here is not the true population mean. It's what we are assuming the population mean is. So in my example, that would be 105. And then whatever sample mean I see from my data set, that's what I'm going to kind of standardize, right? Subtract the mean, divide by the standard deviation. Now here, dividing by the standard deviation, why does this look a little bit different? Well, because remember, I'm dealing with a distribution of my sample mean. So just to kind of give you a little more insight here. So if I want, I think I was using Y on that slide, right? Not X. Yeah. So that sample standard deviation of my sample means would be using the sample variance and then dividing it by my sample size. So when I was standardizing a variable, what was I doing? All right. So if I want to standardize my sample mean, I'll take the sample mean I found. Now I know my sample mean should be normally distributed around the true population mean. I don't know the true population mean, but I assumed the true population mean was 105, right? So I'll divide by the assumed true mean, and then here I should be dividing by that standard deviation. Well, how do I calculate the standard deviation? It's right here. So I'm just kind of plugging things in. Here's the equation that we'd be using to standardize our sample mean values to get now not a Z value, but a T value. Okay. Any questions here before I kind of end? We've got 2 minutes here, so I'm kind of running into it. All right. So what else do I want to say here? So we'll pick up on this next class. We'll look at critical value approaches. So what I'll say based off of where we got. A, I'm not going to put the quiz out there because I know we haven't covered enough, but I don't want someone to start it and go, I didn't realize we didn't cover the material because I wasn't in class or something like that. So I'm going to hold off on posting that quiz until after class on Tuesday. We'll definitely have covered all the review and start working on linear regression in Tuesday's class. That first problem set, though, I would start working on that now. We should be able to work through almost at least the first like 8 of the 10 questions. So you should be able to get a really good start on that assignment. I'm also going to have some additional office hours. Tomorrow I'll be there from 10 to noon. I think I put an announcement up. If I didn't, I'll put one up when I get back to my office. I know I'll be here tomorrow then. If you have questions, we need to make sure that we can get Stata working early on in the semester, not the day before this first assignment is due. You come in and tell me I don't know how to get to work, okay? Other than that, have a fun, safe weekend, and I will see you guys. Oh, I didn't do the in-class quiz today because I ran out of time. Well, maybe we'll have 2 in-class quizzes next week, all right? So I'll see you guys in class on Tuesday.